Hello. In this video, I'd like to share an idea. Simply put, it is sort of an architecture for computation. The idea of this architecture is to be in flexible acceleration for the CPU. To understand how it works, it's important that I give you some background first. We're going to start with this thing called FPGA. I'm not going to get too deep into it. If you want to learn more, I'll be leaving a link to another video that explains FPGAs in depth. Anyways, FPGAs are chips that could do a lot of things like Arduinos and other microcontrollers, but they work in a very different way. FPGAs are composed of this big ass mesh of small little nodes and some wires between them. These nodes are called CLBs, which is short for configurable logic block. As their name suggests, CLBs can be configured to perform many Boolean logic operations. You can turn one of them into an AND gate or an XOR gate or anything like that. These gates are then connected to one another through the wires. These wires are also configurable. More specifically, we can change how they connect to one another and to the CLBs. The idea of an FPGA is to be a sort of a framework for flexibly creating digital circuits. You define some digital circuit using a hardware description language, or HDL, run that through a synthesizer and upload to the FPGA. That FPGA will then act as the circuit you created. It is very important to emphasize that the FPGA isn't just simulating the circuit. It actually is the circuit. Their wires and gates are all actually there, working together all at the same time. Their limitation is usually their size. Size here means the amount of CLBs we have. Mine, for instance, has 25K CLBs. In a funky way, they're analogous to memory storage. The same way you allocate memory to store data, an FPGA allows you to allocate some of it to store digital circuits. Comparing FPGAs to processors, we see that both can solve many problems, but they do so using essentially different strategies. We achieve work in processors by turning that work into a series of instructions that will be executed one at a time. To achieve the same work in FPGAs by mapping that work into digital circuits, whose signals will feed one another. In a way, it is as if processors unwind their work through time, whereas an FPGA unwinds it through space. Of course, each strategy will have their pros and cons. The constant reconfiguring of the processor allows it to execute any random list of instructions you give it, but it isn't really very fast. In fact, processors are really slow. We think the ones we have today are fast just because we have increased their clock speed to as much as physics would allow us, gave them some accelerators to help them in specific uses, and spent decades optimizing them. FPGAs, on the other hand, are way more performant due to their massive parallelism. Their flexibility, on the other hand, isn't so great. If we're doing some specific work, a lot of times, the FPGA is a good candidate. But if you need to do a bunch of different things, each one only once, well, you're going to be spending a lot of time waiting for the FPGA to reprogram itself. In short, processors are great when what you need to do is completely random, and FPGAs are good when what you do has a lot of structure and repetition. But real-life applications are rarely just one or the other. Usually we find both. Sometimes when a specific structure and repetition happen a lot, we create something to help the processor. For instance, 3D rendering requires a lot of matrix multiplications, so we build a processing unit just for that. I call these accelerators. That is good, but now we have another problem. Suppose you have this specific computation you need to run in your application, but your CPU is struggling with it. If you're in luck, there is some accelerator available that you can use to speed things up, but real life is messy. What if you're working with some string reading machine that has a lot of recursion, ifs, and self-references? In this case, I hope you brought something to do while you wait for your program to finish. Since we have both random-like and structured work in everyday computing, naturally I thought that maybe it would be appropriate to have both components present in our systems. Imagine we had something similar to a GPU, but with a big FPGA inside. And while you're loading the process and the files into memory, you'd have some FPGA code that would be loaded into that FPGA card. It would allocate some of the FPGA for the circuit you defined, which in turn would then help you with your specific situation. In a way, it is on-demand hardware optimization. I must test it, I thought. So I bought an FPGA, learned System Verilog, and came up with some tests to evaluate if this option is feasible. Turns out it isn't. That's because the nodes in the FPGA work at a very low level. By that I mean individual bits, and even simple stuff like 32-bit integer multiplication can get big. I remember that when I tried writing a fully parallel 3 by 3 I64 matrix multiplication, the synthesizer requested 1 million nodes. My chip only had 25K. It seems like FPGAs are meant mostly to work as I/O support for microcontrollers or other embedded systems by dealing with communication protocols, signal generation, buffering, bit banging, and stuff like that. Operations ray tracing, geometry collision, or graphics processing require a lot of higher-level operations, like floating point division. FPGAs are out of the question for these. It didn't work, so I just gave it up. Sometime later, however, when scrolling through some news, I saw something about a startup company that was intending to do something similar to what I thought. I dug in, searched through some of their references, and found that there are chips that looked promising, the CGRAs. From what I understand, they're structured in a similar fashion to FPGAs, but instead of simple wires and logic gates, they have buses and nodes that work like ALUs. An ALU, if you don't know what that is just the part of a processor that does the actual calculations. Essentially, they would allow you to lay out a big computation tree through these ALUs, which should be faster and consume less memory. I also learned that the one I was reading about was not the first one. Actually, not even close. In fact, CGRAs are actually quite old. I found some stuff going back all the way to the 80s. So I thought, okay, there's something wrong here. If the idea is good and has been around for so long, why don't we use it nowadays? There must be something wrong with it. Maybe it has been lost in the sands of time, so its potential never had the chance being realized. If that was the case, why are there some papers presenting some ideas for it as stuff like ultra-low power consumption processing? There must be an issue with the concept then. What could it be? The answer, I believe, is that CGRAs are a good idea, but they solve only half of the problem. CPUs do more than just calculations. They also perform some stuff which I am going to call control operations. Control operations are things like branching execution, copying stuff around, managing connection protocols, stuff that has to deal with side effects and self-control. In fact, if you think about it, you're going to see that most of what real software seems to be these operations. Only in situations like gaming, crypto grifting shit, or scientific simulations we find heavy, complex computation. CGRAs can only execute calculations. They don't do control. Yes, they can multiply matrices real fast or calculate some weird-ass composite probability or stuff like that, but they won't be parsing through that heinous XML and writing its data to the database. Okay, we have an answer for why CGRAs aren't that cool, but the problem still stands. We have a gap here. We still need something to be the unflexible, yet fast spatially represented yang to processor Zine. But there is a solution which we're going to build together. We're going to first start with a regular old CGRA as base. Now, we're going to make some changes to it. A CGRA, as was said before, is a matrix of ALUs interspersed with buses. First, Emma, do something that is not related to adding control, which is to change this bus connections to something a bit more reasonable. Instead, I'm going to use a register bank. A register bank is just a bunch of registers. If you don't know what a register is, it's just a small circuit that stores data. Usually a word, which in this case means 32 bits. We keep the ALUs. They can do the usual ALU stuff, addition, multiplication, and bit shift, etc. The registers can be read by and written to by any ALU and will serve as the main form of communication between them. The idea is that the registers store data. The ALUs operate on that data. Having a register bank instead of simple, anonymous buses is important because it will give us the power to manage the data going around manually. Okay, cool. Let's get back to the control problem. I separate control into two categories: side effects and execution manipulation. A lot of side effects involve just reading and writing to the main memory. Some other parts involve talking to peripherals and stuff like that, but I'm just going to ignore these. We're going to give the ALUs the ability to access the main memory. In a real implementation, we would have some form of shared bus interface. This interface would keep command queues and all of that stuff and would serve the ALUs. I'm just going to represent that by giving them two commands that do that directly, write and read. Now, for execution manipulation, the solution, as it turns out, isn't so hard. In fact, all you need to do is add a 1-bit pair of ports to the ALUs, which we're going to call activation IOs. The activation input is kind of a GO signal for the ALU. If we want the ALU to execute, we just set a high. The ALU will execute, and when it is finished, it will set its activation output port to high for a clock. If we keep the activation input high, it will keep executing continuously. After a chain of execution, the last activation output will always be a low value before going back to sleep. If we think about it, the activation kind of works like the execution pointer of a process. When an ALU receives it, it will perform its computation and then forward it to the next instruction. It usually only stays on at each place for 1 clock cycle, unless we want an ALU to continuously be processing something. An activation signal can only be either high or low, so it should need 1 bit of data to be represented. I am not, however, going to give them special registers or anything like that. Instead, these IOs are going to be connected to the data registers and will be converted from and into 32 bits the same way we do in the C language. We do so because it allows us to use the data operations of the ALUs to also be used to process the activations. We are also going to need a new ALU operation, which I'm going to call sync. It is sort of an and with memory. If one of the inputs go high, the ALU will remember that and consider as if that input is still high. When both the memories of the inputs go high, it will output high for a single clock cycle. Then it will forget these memories and the process starts all over. To understand this operation, imagine we have two distinct paths of calculations which are merging at some point. We need the data from both of these paths. We can't just continuously run the merging path, since it might have side effects. We need to execute it only after both inputs are available. We could use an operation on the activations, but remember, the activation signal generally only lasts 1 clock cycle in a specific place before moving on. So if the inputs are not perfectly synchronized, the rest won't execute. To fix that, we add a small memory to the in operation. Now, it is going to remember that one of the inputs has been set when the other goes high, and that we can continue. Lastly, we need a controller. This is the guy that orchestrates the entire thing. It is the one who reads the instructions from the main memory and configurates our stuff accordingly. More specifically, it has the capacity to set up ALUs by defining their operations, inputs and outputs. It can write to and read from the registers, including to its own program counter. And lastly, it can stop and wait for some activation signal. In general, it's going to work this way. Imagine we have this procedure that we want to execute, but it's heavy to the main CPU, so we delegate it to this architecture. To do so, we imagine a way to configure the ALUs and registers so that they will execute the procedure. When it's time to execute it, we give the controller commands to prepare stuff to be as we imagined. The controller does so, sends some activation signal, then goes to sleep. How about we get a taste of it? I'm working on a simulator written in Rust. It isn't complete yet, and I haven't touched it for a while. If you'd like to play with it, leave a comment below. For now, though, all we have is a mental model, but that should be enough for simple experiments. Let's start with a simple for loop because it is an important programming construct that happens everywhere, and that involves branching. The idea is simple. Imagine we have this circuit somewhere else that we want to loop. It will probably be waiting for an activation signal. We ping that signal. It will flow through, executing its steps. All we have to do is then hear the activation output at the last step. We run that activation through a small test that, if succeeded, will be sent back again to the circuit. Think of it as kind of like a sonar. We send a ping, wait for it to reflect back to us, then if we want, send another ping, repeating the process. Okay, let's get our hands dirty. First, let's keep registers 0 and 1 with values 0 and 1, because these constants are useful. Second, register 2 should keep count of how many iterations we still need to run. Register 3 is the start signal, and register 4 is the finish signal. ALU0 is a larger than test. It is always active. It will compare register 2 and register 0 and will output to register 5. ALU1 is in and always active. It will both read from registers 3 and 5 and output to register 6. The value of register 6 will activate both the external circuit and ALU2. ALU2 is set to subtract. It reads from register 2 and from register 1 and will output to register 2 as well. Simply put, it is a decrementer. The output activation will run through the external circuit and should appear again in register 3. Here's how it works. The controller sets reg2 to the amount of iterations we want to run. Then it sets start signal to high for a clock, then to low for another clock, and finally, it goes to sleep, waiting for the finished signal. From here, we repeat this process until the register 2 is 0. In the last step, we need a way to inform the controller that we are finished. Since the finished signal is register 4, the controller will be waiting for it to go high. We set ALU3 as an equals test. It compares register 2 and register 0, is activated by register 3, and will output to register 4. This should be it. That was fun. How about we do another? A DMA is a circuit that does copy-paste. We give it two memory addresses, an input and an output. We also give a length. It will copy the length bytes from the input address to the output address. They are important because copying data is very common. And if we have a DMA, the CPU can just offload that work to it and go do something more complex instead. Let's implement it. First, reg 0 and 1 are 0 and 1 again. Second, reg 2 is the start signal. Reg 3 is the finish signal. Reg 4s the input memory address. Reg 5 is the output memory address. And reg 6 is the length. The idea here is that we create a loop, just like before, with the inner circuit being something that reads from a place and writes into another. ALU0 will be set to read from the main memory. When reading, the first input is the address from which it will read. Here, that is reg 4. ALU0 is activated by the loop. The write operation's first input is the address, and the second input is the value to be written. ALU1 will be responsible for that. It will read from register 5 and from the output of ALU0, and is also activated by ALU0. We also add two loops that will increment both the input address and output address. They are both activated after the write operation and will, in turn, activate the loop. Naturally, the loop will have its own registers and will use the length as the loop counter. This should be enough for our DMA. But let's be honest here, this DMA kind of sucks. Maybe a parallel version won't be dog's hit. The idea is really simple. We get the part reads and writes, and we copy-paste it a bunch of times. Let's say 8 times so that each execution moves 64 bits. We could go for more, to be fair, but for now 8 is good. We have to change a few things. First, the loop won't decrement the length by 1 anymore. Instead, it will decrement by 8. Second, the ULUs that increment the address will also increment by 8. Third, we need to have one ALU calculating each offset. They will read from the input address, and each will have a register with its offset value. We could also chain their values if we wanted to save on registers at the cost of a slight time offset. Finally, since we're dealing with memory accesses, although their addresses are close to one another, we don't have any guarantee they will all finish at the same time. So we need something to keep them synchronized. Remember the sync operation? Here's where we use it. We create a tree of synchronization of the write activation outputs. Since we're working with 8, we're going to need 7 ULUs to synchronize everything. I know what you're thinking. DMAs already exist and are probably better. This isn't really useful. Well, yeah, but hey, race the thing. Imagine we had to do an operation to each of the data points. Suddenly, a common DMA wouldn't do it. We'd have to iterate each byte individually in a regular CPU. This is the kind of situation where this architecture shines. Cases that aren't really common, and therefore will have no accelerator available, but are also being hard on the CPU. This should be everything we need. This is it for the experiments for now. Let's see what we found out. Starting with computation. We need to analyze speed and power consumption. Let's start with speed. There are two things that, in theory, should make this architecture faster than the common CPU. The first is parallelization. This one is an old friend of ours, and we all know it. It means the computer is able to do many things at the same time, which should be faster than doing each at a time. The second is pipelining. The idea is that since the processing pipeline is laid out in space, we can have distinct data points at different stages of the pipeline at the same time. This makes stuff faster because you don't need to wait for the current data point to finish to get started on the next. In our examples, we didn't really pipeline anything, but it is possible to do so. If we had any guarantees on the synchronization, we just use that. If we don't, maybe we could use a sync with a NOT or something like that to keep kind of a queue-like system. What about power consumption? I'm going to be honest here, I'm not entirely sure what affects energy consumption in a CPU, but it seems to me it has to do with changes in the internal state. Basically, you're spinning, when you're turning on and off, a lot of transistors, which makes sense since when that happens, you're either charging or discharging the MOSFET's gate capacitance. Okay, does this architecture reduces energy consumption? Can we slap that little green leaf icon and pretend we care about the environment while we lobby the government to allow us to do more fracking and to reduce subsidies to clean energies? From that point of view, it seems that we can. Think about this. Once we set up the structure, it will remain mostly static, with the exception of the data flowing through it. In comparison, a common CPU would change its state for every operation it executes. Okay, so, in theory, it seems to be faster and consumes less power than a common CPU. That is great, but as the infidel you are, you must be thinking it has some caveats. Well, you're right. It is only useful when there is some form of repetition in the code. Actually, it is kind of middle ground between the base CPU model, which can run any random list of commands, and a CPU accelerator, which can only do some very specific stuff. In fact, it seems like a sandbox for creating accelerators, which is why I'm calling it the FAM, or Flexible Acceleration Module. I think it would be very cool to have some of these modules in a desktop CPU, because it would allow programmers to write their own hardware optimizations. I also have some more ideas for it, like the controller having an offset operation, so that we could have many circuits for different stuff at the same time. It could be the case that for common computers, it doesn't fit well, but it could be of help for embedded system or computer vision applications. In all honesty, I have no idea of what to do with this besides sharing it on the internet. I don't have a lot of money to actually design it and have it fabricated, nor real reason to do so. If you have any ideas, share them in the comments. That's it for today, folks. I hope you've had fun watching this video. I do like to also ask you to give this video a like and comment something. I have some other ideas too. If you want to hear about them, write that in the comments. Thank you for your attention and bye.